Australia in relation to the clarity that he brings to, I guess, representing teachers and representing good practice. So I'll hand over to Greg. The floor is his for the remainder of the day, and then we'll finish with lunch. But I'd like to thank Greg, who came up from Melbourne this morning, and I hand over to Greg.
Cheers. I actually came up from Ballart, so 4 a.m. this morning. Left Ballart in the school car, so I'm still going, but I'm looking forward to getting into bed tonight. Terry's done a good job of introducing me. That's what I was going to start by doing. One thing, so this is me. I've written 3 books. These are the 2 most relevant to what I'm going to talk about today. That's me on, well, it says Twitter, or is it X now? I don't know. But the other thing is, if you're after my blog, if you Google me, you get my old blog, I think, an old WordPress one, which I had maintained for many years. That's now an archive. If you want my new stuff, it's on Substack, feelandpale.substack.com. So I was going to talk a little bit about myself. So I'm a teacher. I started teaching in 1997 in London, and I've been doing it ever since. I came to Australia in 2010, moved to Ballart. I've been blogging since about 2012. I'm a writer, and I did a PhD in instructional design, which is what Terry referred to. There's a paper that I published as a result of that PhD work, and it's on the concept of productive failure. I know there's been a lot of interest this morning actually. It is afternoon now, but there was interest this morning in desirable difficulties, and I actually go into quite a lot of discussion about that, because I think some people see a conflict between desirable difficulties and explicit teaching, and superficially it looks like there might be, but it's about this thing that we call element interactivity in cognitive load theory, and it depends on the level of element interactivity, but we're going to talk about that, I'm going to talk about that later on in this session. And as Terry said, my PhD supervisors were John Sweller and Slava Kalyuga. Sweller, sounds like you know about Sweller. He's an Australian treasure, should be better known, because he's a real sort of hero in many ways of educational psychology. Slava is the guy that discovered what's called the expertise reversal effect, which we will also talk about during today. And here is Dylan William. So he tweeted that in 2017. And I agree with him, but I know Dylan William a little bit, and I've talked to him about this. And I think his reasons for being interested in cognitive load theory are not what you might think. And it's something I'm going to actually talk about, I'm going to address right at the start, because I think it's very interesting. And it is to do with the origins of cognitive load theory. So, can you hear me if I wander around? Do I have to stand there? No? Okay. So, what you've got here is a very early experiment that John Sweller did with a few colleagues before the advent of cognitive load theory. So he hasn't even conceived of cognitive load theory at this stage. And it's a very weird experiment. As many psychology experiments are, it's done with undergraduate students. And basically he gives them 2 numbers. So in the first problem, he gives them 60 and he gives them 111. And he says, right, you've got to get from 60 to 111, but you can only use 2 moves. You can use either move as many times as you like, but you can only use 2 moves. There's only 2 allowable moves. And that is to either multiply by 3 or subtract 69. And you can see in the first problem to get from 60 to 111, you multiply by 3 and subtract 69. Then in the second problem, you multiply by 3, subtract 69, multiply by 3, subtract 69. And in the third problem, and so on. And you can see that there's a pattern there. Yes? None of them involve multiplying by 3 and then multiplying by 3. None of them involve subtracting 69 and then subtracting 69. They all involve alternating those two moves. So he gives them the first three problems, and then he asks them the fourth. And most of these undergraduate students can solve the fourth problem. It takes them a while, though. It takes them a while because they haven't figured out the pattern. Now, you think it's obvious because it's in front of you. But they didn't figure it out. And this got Sweller thinking. It's possible to engage in an activity, correctly solve the problem, but not learn the key underlying structure. And it made me think, when I was a baby teacher back in 97, 98 to 99, I used to teach science. I teach maths now. I've got a physics training, did physics, natural sciences at university. But I used to teach science, and I used to teach chemistry. And one of the things I had to teach in chemistry was the effect of surface area on the rate of reaction. And what you had to do is you had to get these chips of marble which react with hydrochloric acid, and you put the acid in, and you collect the gas as it comes off in a syringe. And basically, the faster the rate of reaction, the quicker the syringe fills up with gas, and the quicker it moves out. And what you do is you record the volume of gas in the syringe. And you plot these graphs and so on. And you're supposed to conclude that the smaller marble chips, so in each experiment, the mass of marble chips remains the same, but you have large chips, medium-sized chips, small chips. You're supposed to conclude that the smaller the chips, the faster the rate of reaction. And my students, I would set this experiment up. It would take, an hour or something. They'd walk around the class. They said, "Where's the gas syringes? Which hydrochloric acid are we using?" And we'd go through it all, and I'd say, "Wipe that up, you've made a mess of the bench." We get all the way to the end of the class, and I say, "Right." So they've all got their graphs plotted. So, right, so what have we figured out from this experiment? Nobody had figured out the principle that the size of the marble chips affected the rate of reaction. And it's a very similar phenomenon to this one that Sweller discovered. And it's made me suggest this idea, which you might call like the first principle, or no one has ever done this. But the idea that students, you can read that. Now, I think this is a cautionary tale for us. And this is the thing that this is what I think is the thing that really struck Dylan Wiliam when he first started looking into cognitive load theory. The idea that students could successfully complete tasks, but not learn what you wanted them to learn. And it's a pretty fundamental issue, because I think that a lot of, certainly in my experience, my past, a lot of planning in schools is what you could call activity-based. So we've got this cool activity, we want to do the activity. I remember at my current school many years ago, someone said, "Oh, I'm doing this activity called Greedy Pig." And it was a maths activity, and it involved getting this big fluffy dice. Dice? Die. It's die, there's one of them, isn't it? A fluffy die, doesn't sound right. Anyway, and you rolled it for some reason down the middle of the classroom, and there was a bit of sort of commotion about this, and there was some rules to this or something, and it was called Greedy Pig. Right? So one of the teachers said, I've done Greedy Pig with my class today, and one of the other teachers says, "Well, I better do Greedy Pig with my class, because I don't want them to miss out." And another teacher said, "Oh, what's Greedy Pig?" And they said, "Oh, well, what you do is you get this big fluffy dice, anyway, and you roll it down the center, and there's rules about, oh, I'll do that with my class." That's activity-based planning. No one was thinking, well, as a result of that, the students are going to learn X, Y, or Z. And I think a lot of planning can take that form. Now, if this principle is borne in mind, we could actually be setting kids up to not really learn very much at all. The assumption that if you're doing something vaguely scientific or something vaguely mathematical, you'll be learning science or you'll be learning maths, I think is flawed. And so this is why I think, and really cognitive load theory isn't much use to you unless you share this opinion. We should start with what we want the students to learn. And then we should select our activities according to that, not the other way around. So that's sort of like the origins story a little bit of cognitive load theory. I'm now going to talk more about the foundations of it theoretically. That sounds very dry. I hope I will get you through this without anyone falling asleep, but we'll give it a go. This is an ancient Sumerian clay slab. And what the ancient Sumerians did is, say I give you, I don't know what they give each other in Sumeria, goats. So I give you 3 goats, yeah? What I do is I get 3 beads and I wrap them in clay because then I can see if the clay is broken. So later on, we can see that I owed you, we can break the clay, we can get the 3 beads out and we can see I gave you the goats. Did you give me the goat? I don't know. Anyway, someone owes somebody 3 goats, yes? So what they then did is they then decided, well, why wouldn't we put a mark on the clay, 3 marks, to show how many beads are in there? And then when they did that, they realized they didn't need the beads because you got the marks on the clay. And this is how the first ancient Sumerian writing evolved, because once they realized they could record things like that, they could record all sorts of things with a little clay stylus, a little wooden stylus in the clay, and you could record stuff. And so this is ancient Sumerian writing. So that's about 5,000 years old. Okay? So that's about how old writing is. Writing has evolved independently of ancient Sumerian, probably most notably in Mesoamerica, but none is older, really, than about 5,000 years. And for much of that time, in fact, it was the preserve of an elite, a clerical elite, often the sort of priest class. They were the only ones that could read and write. Why does that matter? Well, here's my human existence clock. Now, it's a bit rough, this, because no one actually knows exactly when anatomically modern humans first appeared. And when you think about it, it wouldn't have been like, they wouldn't have just sort of popped into existence at one point in time. It would have been a gradual process. But using the sort of estimates, the best estimates I could find on the internet, I sketched this sort of clock for human existence. So if at 12 a.m. the first anatomically modern humans appear, that's midnight. Then it's 10:34 p.m. when you get the first farmers. 11:24 p.m. is when the Sumerian writing appears. And at 1 minute to midnight, that's when we get the start of mass literacy, where we're trying to teach everyone to read and write in Europe. Now, why does this matter? Well, this matters because presumably we have been speaking to each other and listening to each other for hundreds of thousands, possibly millions of years. Presumably, those people who were more effective, more skilled at speaking and listening, were more evolutionary fit. They were able to convince more people to marry them or whatever and have more children, and those children were more successful. And so they passed their genes on, and those that were less successful at speaking and listening didn't pass on as many of their genes. And so we've evolved to a predisposition to speaking and listening. Even if the ability to read and write makes you a more attractive mate, I'm not even sure that's true, but even if it does, the fact that writing has appeared so recently means that we couldn't have evolved a capacity to acquire it. So there's a key difference between these two things. And of course they are related, so they're not completely different, because reading and writing sits on top of speaking and listening. But speaking and listening has potentially been shaped by evolution. Reading and writing cannot possibly have been. And this leads to what David Geary, an evolutionary educational psychologist, has defined as two separate categories of knowledge. biologically primary knowledge, which we've evolved to acquire, and biologically secondary knowledge that we've not. Sorry, I shouldn't have spoken over that. Cognitive load theory applies to the biologically secondary knowledge. And there's a good argument for saying schools were invented to deal with the problem of passing on large amounts of biologically secondary knowledge. In traditional societies, where there isn't reading and writing, there also aren't schools. And a lot of the knowledge can be picked up by a kind of apprenticeship system. But if we want to en masse teach these very unnatural things, reading and writing, and everything else that we do in school, which is kind of based on that, like even you could even think of mathematics as a very specialized form of reading and writing. Studying history involves a lot of reading and writing. So it's at the fundamental level of what we're doing here. That's what schools are for. Now, it doesn't mean schools aren't interested in other aspects, but that's why we have them in the first place. And that's what cognitive load theory applies to. It does not apply to biologically primary knowledge. We should sort of pick that up in a different way. One person editing something I wrote suggested that I should say that we have like an app for picking up biologically primary knowledge. We're sort of predisposed to it. But we don't have that for biologically secondary knowledge. I'm going to press on. Okay. Now, what's that all about? Well, we're going to now look at a model of the mind. But before we look at a model of the mind, we need to bear in mind a word of caution. So, when I talk about the model of mind used by cognitive load theory, I am confronted by people who don't like cognitive load theory for various motivations. They might not like the implications of it. They might genuinely be skeptical of it. There are issues. It's not a finished product. We're still doing a lot of research in that area. But one of the things they will say is, but the model of the mind in cognitive load theory is not true. Because in cognitive load theory, there is no sensory memory in the model of the mind used by cognitive load theory. And that's true. And it's also true that we do have a sensory memory. So is cognitive load theory wrong? Well, actually, that's a fundamental misunderstanding of science and what science is doing. Science develops models that are as simple as possible, but no simpler, and they make predictions, and those models are good as long as the predictions they make are good. And that's what cognitive load theory does. It doesn't attempt to be a full, 100% detailed and accurate description of how the brain works. It's just a model. And it's useful as far as it goes. And that's all it's supposed to be. But it's incredibly powerful. So this is the model. We have this working memory that is extremely limited. We can process about 4 items in working memory at a time. What an item is, I will come back to. We have a long-term memory that is effectively limitless. There must be a limit on what you can put in the long-term memory, but no human has ever filled their long-term memory up, so we don't know what it is. When you're learning biologically secondary knowledge, it has to pass through this very constrained working memory. I used to think that was a bug. I was like, well, why would the mind be like that? That's silly. But it's actually a feature, because your mind has evolved to know that listening to your parents talk to you is important, and you should pay attention to that, and you're motivated to do that, and you pick up language. But all the other things in the environment, it doesn't know what's important and what's not. And this system filters information to make sure that it's important, because if you've gone to the effort of pushing it through this filter of working memory and then trying to retrieve it over and over again from long-term memory, that's training your mind that this information is important. And so what it avoids is rapid and catastrophic changes to your long-term memory that would otherwise occur. So it's more of a feature than a bug. But notice it's really hard to get stuff from working memory into long-term memory, but it's actually really easy to retrieve stuff from long-term memory. In fact, it's often imperceptible. We think we arrange knowledge in long-term memory in terms of their semantic relationships, in terms of meaning. Okay, so this is So this is, what are they? The marsupials and that. This also illustrates that that schemas don't have to be accurate representations of the world. Because the platypus isn't a marsupial, this person thinks it is. It's a monotreme. But it arranges things according to their meaning. And I can give you an example of this. So, 3x equals 18. This is an extremely complex cultural product, what you're looking at now. You've got 4 items, 1, 2, 3, 4. But they all are in a relationship with each other. One of them, the x, represents a number, but we don't know what the number is. The equals sign, not as many young math students think, doesn't mean put your answer there. It means that what is on the left-hand side is exactly the same as what is on the right-hand side. If you want to manipulate this in any way, you have to bear in mind all the relationships. You can't just deal with each element individually, right? It's really hard to teach a student all the things they need to know to appreciate that. Yet most people in the room, within a fraction of a second of me showing you that, knew that x was 6. This demonstrates the power of retrieval from long-term memory. There's a lot that goes into that, but you just knew it. You just activated that schema and you just knew it. Just came to you. And that's also a problem for teaching, because the ease with which we get stuff from long-term memory means that we underestimate the value of having stuff in long-term memory. And we think, oh no, you don't want to stuff that memory full of facts and dates and things like that. You want to focus on critical thinking and being creative. But you can't do any of that without these schemas. That's the stuff they're built on. Because of the time, I'm going to actually skip this discussion about whether cognitive load theory is, what sort of information processing system it is. If we get to the questions, you might want to ask me about that if you're interested. But I'm going to go to this important idea that I foreshadowed at the start, which is element interactivity, particularly in the context of the discussion of desirable difficulties. So, element interactivity is a concept used by cognitive load theory, which deals with the complexity of what we want students to learn. If I said to you, you've got to go away and you've got to memorize all the symbols of the elements of the periodic table, I reckon you'd probably be pretty bummed out by that, because it's going to be difficult to do, right? It's not going to be much fun. But every single item you could process individually. Okay, so you could have a flashcard and, I don't know, borium, BH, you can focus on that one. And then you can focus on hassium, SH, you can focus on that one. They're all separate to each other. So although it would be tedious and maybe not that fulfilling, you could break it down and every single one would be well within the limits of working memory, because each time you're processing one item. In that situation, it might even, because your working memory can process 4 items at a time, it might even be optimal to sort of introduce a little bit of difficulty, a little bit of sort of practice testing from the outset, or maybe give the first letter of the name of the element, and then you've got to complete the rest, desirable difficulties. That's what we say is low in element interactivity. Why? Because the literal elements in this case, it's a bit confusing because we've got elements in a periodic table, which are called elements, but I'm talking about elements in your working memory. But anyway, they don't interact with each other. Now imagine teaching a student how to balance a chemical equation. Whatever you do here has implications over here. You cannot deal with this item by item in isolation. The number of things that you're going to have to process to balance that chemical equation will quickly exceed your working memory limit. Quickly exceed it. And so what you need to do, if you're going to teach that successfully and get students to the point where they can do that, is break it down into smaller bits. Why? We say the element interactivity there is high. However, it's not just a property of, I didn't realize how far back that was now. There we go. It's not just a property of the learning materials element interactivity, because the elementary interactivity of this depends on your level of expertise. If you have a schema for that fires and you just know x is 6, the elementary interactivity of that is low. If you're learning that from scratch, the elementary interactivity is high. So elementary interactivity rolls two things together. It rolls the relationships between the items that you're trying to learn, but also your level of expertise. And if you're an expert, you probably don't want to just have that explained to you again. You probably just want to practice solving problems like that. If you're a relative expert in linear algebra, you want to practice problems. This is the expertise reversal effect. This is what Slava Kalyuga discovered. So one of the fundamental experiments in cognitive load theory is the worked example effect. So you get some students, year 9. You deal with them individually. You bring them into your little room that you've assigned to do the experiment. You give them some worked examples. You then randomly allocate them to one condition or the other. In one condition, they study a worked example and then solve a similar problem. Worked example, solve a similar problem. Worked example, solve a similar problem. In the other condition, those two problems, they solve both of them. They don't have a worked example and solve one, they solve both of them. Then at the end, you see which condition is more effective for learning. And for novices learning something new, like linear algebra, the worked example problem solving is more effective than the problem solving. That's the worked example effect. However, if you've got relative experts, and I don't mean PhD mathematicians, I just mean people who already know lots of linear algebra, relative experts, then they actually learn more from just solving problems. And this is going to have key implications for when we talk about explicit teaching, which we will get to, I promise. We're moving over that. Okay. So before we get on to explicit teaching, it's worth noting, and at this point I could talk about all of these, but I'm not going to. All the different cognitive load theory effects. There's a set of fairly simple ones that essentially involve novices learning new stuff. And these were worked out early on in the development of the theory. And then there's some more complex effects that generally involve that transition from a relative novice to a relative expert and what you do about that. And they do speak a little to what I'm going to talk about in terms of explicit teaching in a minute. So that's your cognitive load theory in half an hour. Now, what about explicit teaching? Okay, I want you to contemplate the next slide. Is this explicit teaching? I'm going to go 3, 2, 1, and in front of your face, if you think it is, I want a thumb up, and if you think it's not, I want a thumb down. Okay? Is that explicit teaching? 3, 2, 1. Okay. Well, there's no right answer to that, really. I mean, if you want to call that explicit teaching, you can. And this is the problem. And this is a problem we come across over and over again in education, is the idea that we're using the same names for different things, or we're using the different names for the same thing. What's that fallacy called? Oh, there's a name for that fallacy. Anyway. And it's a problem we come across time and time again. The thing is, if you're saying that's explicit teaching, which you can do if you want to, it's not the kind of explicit teaching that is supported by evidence. It's not the kind of explicit teaching that came out of the teacher effects research of the 1960s. So you can call it explicit teaching if you want, but that's not the explicit teaching that we've heard so much about, that is going to help improve educational outcomes in this country. And there's all sorts of words. It gets really complicated, this. So there's lots of words in this space meaning different things. Traditional teaching, direct instruction with a capital D, a capital I, direct instruction with a lowercase d, lowercase I, start, lecturing, active learning. And they all sort of float around the same idea. But we need to be clear about what we're talking about when we're talking about explicit teaching that is supported by evidence. So, very briefly, in about the end of the 1950s through to about the early 1970s, there was a whole body of research that took place where researchers would go into classrooms with clipboards and they would try and measure the different teachers' behaviours. So they'd say, oh, this teacher does this, how many times they do it, so on. And then they looked for a correlation between teachers' behaviours and gains in students' test scores. And then they try to identify the things that were associated with those gains. Now, those of you who are into research methods will know that that's just a correlation. So you can't be sure that those things actually cause those test gains. So for instance, for example, it could be that a teacher who's very conscientious always explains to students the purpose of the lesson. And a teacher who's very conscientious gets better results. But explaining the purpose of the lesson doesn't lead to the better results. They're just two features of what the effective teacher does. However, what then happened was that some projects took place where teachers were trained in the things that emerged from this research, and they seemed to become more effective. And then from the 1980s onwards, we got this more drilled down educational psychology, lab-based stuff like the worked example effect and things like that, which also validated the aspects of this model. Probably the best known description of this model of explicit teaching, although he doesn't call it that, he just calls it principles of instruction, is Barak-Rosenshine. I'll give you a minute to read that. Now, you should start to see the connections between this and cognitive load theory. Cognitive load theory, because of our limited working memory, would predict that presenting new material, so we're talking about novices because they haven't seen it before, in small steps with student practice after each step, that's going to be more effective. Okay? So the two things sort of support each other. But also notice some other features. Check for student understanding, guide student practice, provide scaffolds for difficult tasks. I'm lecturing at the moment. I am doing none of that. I'm not asking you questions all the time. I haven't given you all mini whiteboards and asking you to answer my questions all the time. So what I'm doing at the moment is not this. Lecturing is not this model of explicit teaching. It's got some aspects of it. I don't know. Present new material in small steps. Maybe I did that, I don't know. But it's not got those interactive elements. If you came to my place and you walked along McKinnon Wing and all the classrooms, you would see this all the time. Kids putting stuff up on mini whiteboards because the teachers are constantly checking their understanding. That's because explicit teaching of this kind is highly interactive. Less well known is Thomas Good's list, which is based on the same body of research. Brophy and Good did a similar survey, and they called what we're talking about as explicit teaching, they called it active teaching. And if you look it up, they've got something, teacher behaviours and student performance or something, 1984, Jer Brophy and Thomas Good. But this is his list of summarising the same research. So he's encompassed a few more things in there. And some of it, this would overlap in what Tim MacDonald was talking about this morning. I'm going to skip over rubrics because that's a big discussion. So what's the evidence? I'll give you a chance to read this. So, PISA. So the OECD run these assessments every 3 years PISA assessments, and they do a range of interesting things. They assess students in reading, maths and science. I think the assessments that they set are poor, and I actually think that the Timms and Pearls assessments are better, but nonetheless, it's still a bit of a goldmine of information. They also survey the students, and they survey them on all sorts of things. So they survey them, for instance, on what it's like in their classrooms. One of the things I ask them about is whether the classrooms are disrupted and disorderly. And unfortunately, when they ask Australian kids that question, we end up about 69th out of 73 of the states that they ask in terms of the level of behaviour in our classrooms. But they also ask them what kind of instructional techniques they're exposed to. Now, bear in mind that PISA define good teaching to be student-orientated. That's their definition. That's part of their definition of good teaching. And then they go on to say what that looks like. And then they go and ask students whether they experience student-oriented instruction. And the students say, yeah, we do. And when they say that, their performance is worse. And this is because the dominant theory that we are probably reaching the back end of now, but has been dominant for the past 20 or 30 odd years, is this idea of a student-orientated form of instruction where kids figure things out for themselves, they construct their own knowledge, they learn through talking to each other, they learn through interacting with experiments or with simulations or by doing their own research and things like that. And all those sorts of things factor into this idea of a student-oriented curriculum, and it leads to the worst performance in maths, very clearly. Not quite as clear in the other subjects that PISA assesses, but very clear in maths. Then, this comes from 2010. 2015, they did the same thing with science. And asked students about their science instruction. And again, people can debate this, and people will debate me on Twitter about this, and it's all great fun. But the more inquiry-based the science instruction, which PISA thinks is good, the OECD thinks is good, the more inquiry-based it is, the worse the science outcomes. Why? Because this idea of... Now, I don't like the term student-oriented because I think I'm very student-oriented. When I teach a class and I ask a question, and I've got a class at the moment, 47 students. So I've got... we do a specialist maths elective in year 10, and everyone's suffering from a bit of a teacher recruitment crisis. We're a bit thin on the ground. We've got some maths teachers coming, but they're not here just yet. So I'm teaching this elective to 47 kids in a lecture theatre. But every question I ask, mini whiteboards. And I can see exactly who understands me and can do what I've taught, and exactly who does not, and I can intervene. I think that's very student-orientated. But it's not what this means. This means these sort of inquiry learning, discovery learning type practices. And they don't work because they're treating novices as if they're experts. And there's a fundamental difference between novices and experts. We've seen this time and time again today in our presentation, in this presentation. Now, something that works for novices, worked examples, doesn't work for experts. Experts need something different. So this idea, and it's a prevalent idea in education, that we can somehow bypass all the hard work that it takes to get from being a novice to being an expert by just taking novices and getting them to behave like experts, is flawed. Yes? We say, oh, well, real scientists, they do experiments and they figure out things for themselves. So we'll get these kids who don't know any science, and they can do experiments and figure out for themselves like a real scientist. Doesn't work. Why? It overloads working memory. Real mathematicians, they solve complex problems, real-world problems, with lots of different factors that they have to take into account. So this diet that we're giving the kids of drill and practice in class, it's inauthentic. It doesn't represent the real world. It's not what real mathematicians do. So what we need to do is we need to stop doing that, and we need to start to get them to behave like real mathematicians. And of course, if you do that, they get confused, and they get frustrated, and they don't know what's going on. And the parents ring up and say that they're not learning any maths, and do you know any tutors? Because it doesn't take into account cognitive architecture. Here's Jean Chall, again, talking similarly about this process product research of the 60s. So she's slipping into this traditional term. And that's what she's talking about there. But again, it's this same idea. It's being explicit, being upfront, explaining things fully, breaking them down. And this point that's in bold at the end, you hear a lot. So at the moment, there's a big controversy about, in California, they've got a new maths framework. And it's been worked on by a number of people, including Joe Ballart, who is probably the world's most famous professor of maths education. That sounds like an odd thing to say, but she probably is. And they've tried to design it for equity. That's the big thing, big pushing. We want equity. We want all students from different backgrounds to be able to engage in maths. But the things that they're suggesting, the kind of inquiry-based approach that isn't really mandated but sort of suffuses the whole document, it's going to be the most damaging to the least advantaged kids. If you've got cognitive resources, if you've got economic resources, then you can mitigate the effects of poor instruction, because you've got family who can explain things to you. You can probably figure things out yourself because, luckily enough, you've got those cognitive resources. If you can't, maybe your parents can get you a tutor. It's not those kids who suffer the most from a student-orientated, in inverted commas, because I don't like labelling it that way, environment. It is the most disadvantaged kids, the ones for which school is really the only chance they've got, the only source of this education. And if we mess that up, they lose. So I've already sort of answered this. This is just that same slide again. Sorry, I wandered off slightly how I intended to do it. But here's my definition of explicit teaching. Actually, I've refined this slightly for a paper that we've got coming out, hopefully, if it gets past the peer reviewers. But this is basically it. So explicit teaching is a whole process. It's not an episode. It's not something you can do a bit of in the middle of something else. It is everything. It's the whole process of going from novice to relative expert. And again, I just want to make the point, I'm not talking about 6-year-olds to PhD students. I'm talking in any particular domain, you can move from relative novice to relative expert. So we'll have year 8 students, for instance, who are relative experts on linear algebra. And they'll need to solve problems on linear algebra. And you'll have university students who are novices on solving differential equations. I'm talking about maths. Sorry, I keep going on about maths. But this is what this is about. So it's a whole system. So the point is you start by fully explaining things, but by the end of the process, you guide practice, you hold kids very closer for longer. One of the things I've learned about my own teaching, I used to present 4 or 5 different examples, and then I get students to do some problems that are kind of similar but not exactly the same. I don't do that anymore. I present an example, they do one exactly the same. I present another example, they do one exactly the same. And we gradually release that. Obviously, that's a maths approach, and you can't map a maths approach onto every other subject area. The only people that can figure out exactly what the best explicit teaching looks like in a subject area is subject area specialists. There's only so much we can do when we bring the whole staff together for professional learning. There's stuff that has to be worked out by subject area specialists. But it's this whole process of a gradual release of control from the teacher to the students. And that's what's important. And so if we're using that definition of explicit teaching, one which I would argue comes from all the research evidence that we have, then it can't be a little episode in the middle of something else. And this is my little explanation there. So I haven't spoken about big DI. Big DI is we use some of them at my school. Zig Engelman's developed programs, University of Oregon, which are essentially scripted, and they have workbooks that the teacher uses, and there's a whole theory of how those programs are designed. That's essentially a form of what I'm talking about, but it's not the only thing I'm talking about. And then things like lecturing, any kind of teacher-led instruction, they sit outside of that. Explicit teaching is a subset of that. It's a special type of that that's highly interactive and that involves the students a lot as you go along. To allow time for questions, let's have a bit of fun. Let's do a bit of true or false, and then we might skip to the questions. I've got loads of slides here. I could go on all afternoon, but I won't. So this one again. Now, last time you didn't do it right, I have to say. It wasn't quite right. When I go 3, 2, 1, yes, when I'm saying 3, I don't want to see your answers. That's not what I want to see, because then other people are going to look around and say, well, they did that, so I'm going to do that as well. Okay? So I want you to be, until I say show, yes, then you can do that or that, okay? But not until I say so. And not after either, thank you. Okay? So exactly when I say show, thumbs up, thumbs down. Which of the following statements align with the assumptions or findings of cognitive load theory? Let's have a go. So here's the first one. Think. Three, 2, 1, and show. Correct. Yes. It's not our working memory that's effectively limited. It's extremely limited, our working memory. Now, this one I have addressed, but it was very low key, so we'll see if this one got across. Three, 2, 1, and show. That's actually false. Let's go back to the bit where I was talking about the periodic table and learning all the elements. And I said because it's only one thing at a time that you have to pay attention to, you might actually want to increase the cognitive load a little bit, because you might want to just give the first letter of the name of the element rather than the whole, and the students have to work it out. Because one item to process is actually a bit low. We want to optimize cognitive load. We don't always want to minimize it. When you're doing most things that we do in schools, actually, that tends to overload working memory, so it's probably a good heuristic to try and reduce it. But there are some things like learning lists, learning dates, learning names, things like that, where you might want to intentionally increase the cognitive load. Desirable difficulties. Okay. I haven't addressed this one at all, so I'll be interested to see what people say. 3, 2, 1, and show. Yes, I think it's sort of common sense, this, but it's not borne out by any evidence. Probably the best experiment that tried to test this was David Clark and his PhD student, whose name escapes me. They did this series of experiments where they taught kids about the need to control the variables in a scientific experiment. It's deeply ironic, this, given that so much educational research does not properly control its variables. But anyway, they taught kids the need to control variables. Some they used a discovery learning approach, some they used explicit teaching. Unsurprisingly, those students who had the discovery learning approach, fewer of them learnt the principle. That's unsurprising. But what they then did with those who had learnt the principle, either by discovery learning or by explicit teaching, they gave them science fair posters to evaluate. So this is a transfer task. So kids have done an experiment, they make a poster. Is this a good experiment? The kids who had learnt the principle through discovery learning were no better at evaluating these science fair posters than the kids who'd learnt it by explicit teaching. We can't seem to find a benefit of figuring out for yourself. And I give a commonplace example of why this might be the case. So a few years ago, when I turned, when I turned 40, which was probably more years ago now than I'd like, I bought myself a kegerator. Now, a kegerator is what you put homebrew beer in, right? And it's got like a tap, and you've got a gas cylinder and all this sort of stuff. And so to put it together, I watched a video, and the guy on this video was naturally a very good explicit teacher. He explained all sorts of things. He said, you're going to get annoyed because there's all this tubing, right, that connects the gas to the whatever. But don't shorten it. People shorten it. Don't shorten it, because if you do, it won't reduce the pressure enough and your beer will just be froth when you pull out the top, so don't do that. So explain, he gave me examples, but he also gave me non-examples, explained it all. I put this kegerator together. I was very confident in its operation, and I was very happy with it. Around about the same time, the toilet broke. The flush mechanism broke. And so I went to the plumber and I said, I need a little bit of plastic about this big for oh, we don't sell those. You're going to have to get a whole new flush mechanism. So I got it from Bunnings and I'm putting it in, and the instructions are barely existent, right? So it takes me a while. I flood the bathroom a little bit, then I know what I'm doing. So I'm discovery learning here. I'm figuring out how to put the flush in. For the next week, I was nervous that the bathroom was going to flood at any time because I'd done it wrong. Was I better off discovery learning how to fit that than having a plumber do a video for me or stand next to me and explain exactly what I had to do, why I had to do it, why I shouldn't do it this way, why I should do it that way? No. So I think this common intuitive notion that when we just learn things, figure out things out for ourselves, it's better. Look, I'm going to, you know what, I'm going to stop. Because otherwise there'll be no time for any questions. Okay, so we've got about 7 minutes for questions. Madam?
What is it, do you think, in terms of fulfillment, do students get more fulfillment if they figure it out themselves?
Well, I didn't when I fixed the toilet. So, I know. So this is the motivation argument. Is discovery learning, inquiry learning more motivating? Well, I think it could be. And I think one of the things that we have to pay attention to is variety. I think school shouldn't be the same thing all the time, every day. But I also think that people have misconceptions about motivation. So, for instance, everyone is concerned about, everyone wants girls to fall in love with science and technology. That's a big thing. And you see these projects, and what they do is they will get famous female scientists, or maybe not so famous, but female scientists, and they'll go to schools and they'll stand in a lecture theatre like this and they'll talk about their work and they will motivate these young women to be interested in science. And then the theory is they'll go off and with this motivation they will study science and they'll be successful and so on. And I think we've kind of got that the wrong way round. When you look at the motivation research, it's more the other way around. It's more that when people get good at something, when people get effective at something, when people notice that they're getting better, then they become motivated. So if that's true, then there isn't really a conflict between the most effective methods of teaching and the most motivating methods of teaching, because if to be motivated you want to get better at something, then you want an effective teaching method. But I do take the point that doing the same thing all day, every day, like in science, I don't think that science experiments are the ideal way of learning science because there's too many things going on. But I would not get rid of science experiments from a science program because I think it's something that kids really love about science and doing science in school. Yes?
Do you think there's a difference between, like, there are different types of learners? I mean, or are we just teaching them how to be better explicit instruction learners?
Different types of learners.
So like one person might prefer, or is it just because they haven't learned the right way yet?
Well, I mean, probably the most famous expression of the idea of different types of learners is that people have different learning styles. And that's a theory. Well, if you ask students, do you prefer to learn visually? Do you prefer to learn auditory? They will express a preference, there's no doubt about it. But there's no evidence that matching instruction to those styles has any benefit at all. And this is probably because the most important thing is that the form of instruction matches the thing that's being taught. So if you're trying to teach students the structure of the heart, you want a diagram. Like, even if they express a preference for auditory learning, they're not going to learn it as effectively as they are from a diagram. So But at a more fundamental level, of course, everyone is different. I wonder whether we have overdone that, though. I think we're a bit we're into this kind of hyper-individualization where we want to treat everyone very differently because we want to be respectful of them. And I think that's a peculiar facet of Western culture at this particular point in time. The educational psychology research would suggest that people have a lot more in common in how they learn than they have differences. And so you can actually leverage that and teach to what they have in common rather than constantly because it's quite difficult if you've got 25 kids in a class who you believe all learn differently, well, what are you going to do? Like, there's still only one of you. So it sort of talks us into these impossibilities, I think, if we take it to the extreme. Next question. I did have something else to say on that, but my mind's gone blank. No more questions? We done here? Everyone wants lunch? No, go on. Yep.
I don't really know anything about play for young children,
Yep.
except that it's important.
Yep.
How do you think that relates to that idea around discovery?
Yes. Well, I think play is incredibly important, and it's incredibly important for learning biologically primary knowledge. So the stuff that we've evolved to learn, we've evolved a lot of what we've evolved to learn through play. So social interactions, navigating the local area, even possibly aspects of hunting, folk psychology, folk physics. We pick a lot of that up through play, and it's incredibly important to young children's development. So there's nothing in cognitive load theory that would downgrade the value of play. I think where we get confused is so if you don't recognise the difference between the things we've evolved to learn and these much more recent cultural inventions, you end up saying things like, well, kids learn to speak by just sort of being immersed in people speaking. So that where they can learn to read by, we'll put them in a room with lots of books and we'll read to them. But they're different. So like we've evolved to learn the one thing, but we haven't evolved to learn the other. So if you want to use play, say, to learn physics, not folk physics, but physics, I think you'd be in trouble, because I don't think that that's what play evolved to do, because physics is a very recent cultural invention. So there's nothing that would downgrade the value of play, it's just what it's for. And really, this whole discussion is about what we're trying to do here. If we're not trying to teach kids biologically secondary knowledge, then explicit teaching and cognitive load theory aren't relevant. If we want them to have a nice afternoon at the theme park, yes, this is not relevant to that. And that might be something we want to do as part of our school community sometimes. So it only becomes relevant when we're trying to teach biologically secondary knowledge effectively to students. No more questions. I think the lunch is beckoning.
So that we can have a long lunch and then people can go and leave as you so choose. Lunch is at the back in the arcade. It's all ready to go. There are 2 tables there. Can we not just have one line? We have 2 lines. 1 line at each table would be fabulous. Thank you very much to our presenters today, and thank you everyone for coming.